Okay, welcome everybody to our August edition of the ABA Engineering Academy's webinar. This is our August edition. We do these things every month, and it's sponsored by the ABA Engineering Academy. And we want to welcome in our co-host today, John George. Where are you today? Are you on the road or are you
Well,
at
I'm
home
on the
again?
road. I'm on the road again. I'm not too far from you. As the crow flies, I'm in Gainesville, Florida for a few days this week doing some work and watching tropical storms pass by.
Oh, okay. You have any words of wisdom for us this morning?
Well, I will remind everybody that the 21st of this month, which is just a few days away, you need to be sure that your certificates are updated for your SAGE and DASDAC EAS units. Otherwise, you will not be receiving your CAP test each week. And that's something you need to keep up with. There's no charge for that update. It's an easy download. I'm sure many of you have already done it. If you have the Gorman Redlick box, there is no update required for that one. But as a security issue, the way SAGE and DASDAC handles their security in their units, that update is required. And so that's kind of my words of wisdom. And I'll turn it back over to you, other than to say we're glad we have Mike Patton with us. I had the pleasure a few years ago of visiting Mike in his office and facility in Baton Rouge, and quite a nice setup, Mike. And Mike's also bailed my butt out a few times for components for transmitters that I have needed. So again, glad to have you with us today.
Thank you. We try to provide a valuable service to folks.
Larry?
I forgot to unmute my microphone. That's pretty sharp, isn't it? I want to remind everybody that we actually have a sponsor for our academy, our webinar series. It's Max Connect. If you haven't looked at the Max Connect, this is a unique system that you can use to send audio over IP, a secure IP, dedicated IP system from point A to point B. So if you get a chance, check that out at www.maxconnect.com. And as John said, our special guest today is Mike Patton. Mike is with a company out of Baton Rouge, Louisiana, Mike Patton and Associates. I've known Mike for a long time, like John was talking about. We've worked together on several projects. As a matter of fact, we did a 50 kilowatt 4-tower inline array over in Georgia several years ago, which was really a treat. So I want to welcome you into the program, and we'll just switch the program over to you, and you can start and carry on from there, Mike.
Thank you. Thank you very much, Larry and John, and glad to see so many people participating here. I see many names I recognize and a few I don't. Larry has asked me to speak today on directional antennas. It's a subject that we've been dealing with for a very long time. It's often considered voodoo by many people. It's really not. It's coils and caps and pushing electrons around. But, and I suppose photons too, that's the point. But it's often misunderstood. And unfortunately, it's becoming more arcane as a lot of the older engineers are graying out, they say it, aging out. And very few new DAs are being built. The last time I built a new DA was maybe, the better part of a decade ago. What we're seeing more and more of these days is sites consolidating, diplexing, triplexing. There's even a quadplex that I know of up in Minnesota. Alex Hartman takes care of that very competently. I can't imagine what that thing must look like. I was up there a couple of years ago for 2 transmitter retunes in Minneapolis, and I wanted to get up and see Alex. I didn't make it, but I'll probably be back before it's over. They seem to think I have some skill at retuning and rebuilding transmitters, so I keep getting sent around the country doing that sort of thing. And I'm not going to complain, but what I'm going to do is I'm going to just basically cover the basics to begin with. The directional antennas are something we can talk about all week, and I don't have any illusions that I'm going to be able to cover the whole thing in an hour. And many of you, as I see from your names, and I know you, know directional antennas, and probably much better than anything that I could cover in any short period of time. I'm sure you could teach me a thing or two. So, but for people who not as familiar with it as others, we're just going to touch on the basics. Then we're going to talk about how the rules have changed, some streamlining, the method of moments proofs, and then diplexers, because those are things that are fairly new and should be on everybody's radar. We're probably all going to have to deal with in the near future. So let me see if I can make this work here, and I'm going to start my presentation. And let's see. Yes. Oh, look, I believe that worked. All right, so if I can get the space bar to do it here. All right, so did it work? Ah, there we go. Oh, back one. There we go. Okay. Just basic concepts for those who are not familiar with it. A directional array for an AM station requires multiple towers. One tower, unless something is very wrong with it, always radiates a omnidirectional pattern, equal power in all directions. But in order to make a pattern to produce more power and more signal in some directions than in others, to protect stations on the same frequency, so we could fit more stations into the band, which is a brilliant idea somebody came up with a long time ago, and then we ended up with too many stations. But we're seeing that winnowed back down now. More and more stations, unfortunately, are leaving the air for good. That's cleared the band out for those that are able to survive. That's not necessarily a bad thing. But directional antennas work because radio waves act like waves. They can add constructively or destructively. If they add constructively, they make more signal, a lobe. And if they add destructively, they cancel each other out and they make nulls. We can use a combination of the placement of the towers relative to each other, the distance between the towers, the azimuths, the bearings between them, and the amount of power we feed to each tower, and the timing or phasing of those signals to create the pattern that we want. A note is that the technology for AM directionals was developed fairly early. As I understand it, back in the 30s, the concepts were even older than that. The first DAs were built in the 30s, and we've learned a whole lot about RF propagation and analysis since then, but some of the rules that we're stuck with from very early on for analysis of things of that nature are not how we would do it now if we were going to invent this science from the ground up. The rules have been streamlined quite a bit over the years, and then we'll talk about a couple of the ways that that's occurred. But we're still stuck with some very cumbersome methodology as the basis of it, because it was based in that fairly early and, by our standards, primitive understanding of RF analysis and propagation. A DA consists of a phaser, which is a big box in the transmitter building that splits the power to feed each tower and gives us some ability to control how much power goes to each tower, and the relative timing, phasing of that power. I have seen phasers that had no adjustable controls, that everything was moved by a tap. There was a famous engineer out of Dallas many years ago, Earl Cullum, and he was infamous for building phasers that you had to move a tap to change everything. Stable as hell, but very difficult to tune. But almost every phaser I've ever seen has some sort of front panel adjustable controls. The output of the phaser fed through coax cables or open transmission lines. You don't see that much anymore, but you do see it every now and then, especially for very high power stations, mostly overseas or shortwave stuff. But there are a few stations around the country still using open wire transmission lines to carry the signal to each tower. Then at each tower, there's an ATU, an antenna tuning unit, to match to give a good load to the coax and still match the relatively arbitrary impedance that the tower bases present, and also to prevent lightning from coming back into the system and things of that nature. Then the whole thing is monitored with a sample system. The sample system consists of some sort of sampling device at each tower. These, in the old days, there were loops mounted on the tower that picked off a small amount of current. Those have gone out of favor. They're still required on certain arrays, but almost all, I won't say all, of the arrays out there, a bit more, use little toroidal transformers, mostly made by Delta. Phase Tech also made some. I don't think anybody else made any that I'm aware of. That again picks off a small sample of the current going to the tower. Little bitty coaxes, 1/2 inch, 3/8, sometimes even 1/4 inch, carry the signal back to the building. And then there's an antenna monitor, a device that shows you the relative levels of the samples and their timing or phasing relative to reference tower. And then stations that have a different pattern day and night will have some way to switch components between the powers, RF contactors, big high voltage relays, mostly noisy and fairly reliable, but not infinitely so. And then some sort of control circuit to verify that all the contactors have done their job and that the arrays are properly configured. This is just a typical phaser schematic. This is a site we built in Pine Bluff, Arkansas a few years ago. This is the phaser. I don't know if my cursor will show here or not. Do you see my little cursor? Yes, no, maybe?
Yeah, we got it.
Okay, good. So there's the contactor to switch between main and aux transmitters. There's the contactor to switch between day and night. These are the common point matching networks for day and night. And then here are the coaxes to the 3 towers, the contactors that switch between the day network for each tower and then the night network for each tower. I think the day was only was a day of 2? No, they were three. Each pattern had 3 towers. So, there are the adjustable coils for phase and ratio for each tower. The reference tower here did not have a power divider coil because it had so much power than the others. We just left it as a load on the bus and then tapped everything off from there. This is very typical. And then this is one of the ATUs out of that array, another contactor, the day matching network, the night matching network. There's the toroidal sample device and the coax back to the antenna monitor. Day and night, it's the same contactor. It's just two separate sets of contacts on it. And then the tower static drain. So fairly straightforward stuff. As I said, back in the 30s, the original methodology required many field strength measurements, easily a couple of hundred for any sort of complicated array to average out. And there was a methodology. The methodology is still there. It's quite cumbersome. It's a lot handier now that we have spreadsheets, things of that nature, to determine the actual signal radiated along given directions. The nulls were limits. You had to have the signal in that direction below the limit in order to not interfere with the other stations on your frequency or on adjacent frequencies. Lobes, the major lobes, sometimes the minor lobes. I've seen stations that had as many as 15 radials they were required to measure, sometimes only a few degrees apart. If they had different patterns day and night, you'd spend weeks in the field making field strength measurements. And that has been streamlined several times over the years to the point now where it's pretty bare bones, even for a conventional proof, but it's still quite cumbersome. When you build a new array or you make major changes to it, like you add a tower or you replace the ground system, you have to do a full proof, which involves a lot of close-in measurements. Even that's not as cumbersome as it used to be. I've literally built an array where we had to start at 2 miles out and walk into the array with a rope for this pre-GPS every 1/10 of a mile and make a measurement and write it down, and slogging through swamps and woods and snakes and bogs and everything else to develop enough measurement points to perform an analysis for full proof. It's not that bad anymore. Even a full proof, you can get by with about 8 or 10 measurements within 2 miles. And if you're in any luck, you're not in the middle of the deep woods, it's not that bad. It's still not fun. But a partial proof, which is mercifully most of what you have to do these days, even if you're doing a conventional proof, is at least 8 measurements on each radial, minimum of 4 radials required. And in many arrays, that's all you need, between 3 kilometers and 15 kilometers, which is like 2 miles to 10 miles roughly, from the site. The point of most directional antennas, of course, is to be near a city. So typically you have enough of a road network to where obtaining this number of points is not that much of a hassle. Of course, if you're building a site out in the Everglades, and there are some, in fact, I'll be seeing one in a couple of weeks, a little bit harder. You might have to do some explaining to the alligators, but that's a conventional proof. Yeah, even at its best, even today, it's still fairly cumbersome. So about, I guess it's probably been in the works for a very long time, but about 15 to 20 years ago, some of the top people in the business, some of whom are unfortunately no longer with us, got together and developed computer models and worked very hard to correlate their models against the real world. Of course, that's the crucial in any computer model, is to actually make sure that it corresponds to reality. Otherwise, what's the point? And they developed a methodology for calibrating computer models against the real world, and convinced the FCC that it was accurate enough to allow the models to be used in lieu of conventional measurements. And this was known as a method of moments, or moment method. I still call it method of moments because I like the acronym, the MOM proof. And as I recall, the first MOM proofs were that I saw done were right at 10, 12 years ago. I was involved in one up in Memphis, and I'm sure there were others before that, but that was about when they kicked in. If anybody has more accurate information on that, you're welcome to correct me. The MOMs have several advantages over conventional proofs. And we'll get to those in a minute. But here's how MOMs work. That with a device to measure impedance using a small signal generator. I have a device made by a company called Array Concepts in Dallas. Unfortunately, they don't make that model anymore, but you could do it a number of ways. You could do it with like a 25-watt transmitter and a conventional VNA, like an HP 8753. Gary Cavell for years and years did it that way, and I'm sure many others. Lots of ways to do it, but you make a measurement at the base of each tower with all the other towers open or shorted. It depends on the height of the tower. And then you kind of work backwards from that. You have to take into account all kinds of things, like the parasitic capacitance of the base insulator and the inductance of the feed line between the ATU output and the tower base. But you massage it and play with it till you have something that you can defend mathematically and say, this is the actual base impedance of this tower if I were to measure it at that point and nothing else was there. And then you can take that and plug it into analysis software and say, well, if I make this current at this phase into this impedance, then I must make pattern Y. And we know what the pattern needs to be because the FCC, the construction permit generated by the FCC, gives you the limits, and you work backwards from the model to make that. The model spits out a set of parameters. It's kind of an iterative process. I don't think anybody's actually developed software that'll run it backwards to where it'll take the proof and then give you the parameters. My experience is you have to keep plugging values into it until you get a set of parameters that gives you the model pattern that you want. And I may not be the world's smartest crayon on that. I'm not, but I get by. But now we have a model. Now we can defend it. We can show an analysis that we could convince the processing engineers who don't ever see the real world. All they see is their models at the FCC. So sometimes you have to do a little convincing, in my experience. but we could take that set of parameters, dial it into our antenna monitor, and we could say and defend and have the FCC agree with that we have now created the pattern that the construction permit specifies. There's a lot of links in that chain, but we have all agreed that this is a methodology that correlates well enough with conventional field measurements that we're confident that it works. We may all have just agreed to something that may be less than reality, but we've agreed on it, and it works well enough in the real world where we don't see people who build arrays with bomb proofs all of a sudden bleeding over all of their neighbors. So if it is a fiction, it's a fiction we've all agreed to settle on, and it works well enough. The enemy is the perfect is the enemy of the good. It's good enough. But even with a bomb proof, you still have to make a few field strict measurements. It's typically 3 on each of the patterns minima and maxima, the nulls and the lobes. And note the locations, write the readings down. You have to submit that with your proof, but you don't get it back in the license, unlike conventional monitor points. So you have to keep those on hand somewhere, because if you ever needed to verify that your array was still doing what it was supposed to be doing, you need those measurements in order to compare. Now, when you build a proof built on a MOM array, it's a little bit different from a conventional array. Let's talk about how to tell that your array is happy. Traditionally, you would have monitor points. You'd have to measure the monitor points on a regular basis. Used to be the regular basis was specified. Now it's not. It's just as needed. I know stations who've decided that as needed was about once a decade. Others typically once a quarter as the seasons change. But if your sample system fails, it'll give you incorrect readings. And if you, till you go out and read either your reference measurements if you're a MOM proof, or your monitor points if it's a conventional proof, you don't know whether the sample system's failed or the array itself has failed. And so that brings us to the first rule of a DA repair: thou shalt not crank on the phaser. Because the idea that something has drifted and should be corrected on the phaser is probably the last thought you should have. The first thing is my sample system okay? Let's go read the monitor points. Let's go read the reference readings. Let's start digging into the sample system. And I got burned on that just last year in Birmingham on an array where I won't go into the details, but we had a feed coax failure, a backhoe fade, if you will. And we also had a simultaneous sample line failure. And I assumed that another feed coax was bad when it wasn't, because there'd been a sample system failure, a connector with water in it up on the tower on a loop. And I ended up making some fairly bad decisions based on the assumption that 2 things couldn't have happened simultaneously. Well, they did. And in the end, everything worked out. But yeah, don't ever assume that the sample system is telling you the truth until you've verified. Because one bad component, one connector with water in it, one weed-eaten coax, and you don't know where you're at. You're at sea. So you always document where you came from, document any changes, measure it one step at a time. Don't go in there like the cowboys, shoot first and ask questions later, or you will make it much worse instead of better. All right, in a MOM proof, the sample system is absolutely the only arbiter, because you don't have monitor points. The reference points are theoretically you should never have to measure unless something has really gone south. So the requirements for a sample system are much more stringent. The coax cables all have to be exactly the same length, and you have to prove that with a specific methodology of analysis in the rules. The sample devices all have to be proven to be calibrated to each other. Again, and that's part of the submission. The antenna monitor has to be freshly certified that it's calibrated and meets standards, because the sample system is your only arbiter of the truth. In a conventional analysis array, you were able to prove that the patterns were right by the analysis of the field strength measurements. Then you work backwards from that. And as long as the sample system gave you parameter set X, it didn't matter what the parameter set was because you knew that made the pattern. So you were good. But in a mom proof, the only confidence you have that you are making the pattern that your license says you need to make is the parameter set developed from the model that's on the antenna monitor. So if that changes and you don't know why, then you have no way to verify that or you have a very poor way to verify that the pattern is actually producing the what you expect it to be. So you come into a mom-proof array and you have a problem. You see that the parameter set's not what it should be. Again, don't go cranking on the phaser. Go verify that the sample system is right before you do anything else. And sometimes this is not fun. It involves people up on the towers. If you've still got conventional loops, sometimes you have to take the loops off and rebuild them on the ground and put them back. You have to feed the sample coaxes end in and make sure that you don't have a whole lot of loss in one. You don't have phase shift issues. You have to measure the length. There's all kinds of things you have to go through, but always be sure your sample system is happy before you make any other assumptions, before you make any other changes, because you will get burned in a hurry. So why it's good to have a mom. I have a mom. Actually, I had two moms, but that's another story. They are cheaper mom proofs than full proofs. And by the way, a mom proof is always the equivalent of a conventional full proof. There's no such thing as a partial mom proof. There's just one flavor. Obviously, it eliminates any requirement for periodic monitor point measurements. Monitor points have been kind of the bane of directional antennas over the years. As much as sometimes it's fun to get out of the office and say, I'm going to go take my field strength meter and run around. They end up, the environment changes. I've had monitor points that ended up being in the middle of a Dunkin' Donuts or in the median of an interstate where it was patently unsafe to try to measure them. One of my favorite monitor points, though, many years ago, and as far as I know, it's still there in Lafayette, Louisiana. There was a monitor point in a cemetery, and in the original write-up for it, the author of the proof said that he was confident that this point would remain undisturbed for a considerable amount of time. So there's that. But another thing about mom proofs is that it allows you to mostly ignore re-radiation issues. Towers and even other structures, sometimes like water tanks near an array, can act as parasitic radiators. If anybody's out there who's a ham, and I know many of you are, you know how parasitic radiators work in ham antennas, but they will distort the pattern. If it's close enough to the array to actually show up as a mutual impedance in the model, in defective base impedances, then that gets taken into account when you build the original model. I'm not quite clear on exactly how accurate that is, but that's the theory as I understand it anyway. But in a conventional proof, this re-radiating structure will definitely affect any measurements made in its vicinity. As you walk away from it, you can actually see the sine wave of re-radiation from it, sort of a damped sine wave, add or subtract from the incident signal from your array. But this is a local effect. And this is something a lot of people miss out on, is that the only thing that matters in a directional antenna, the whole point of a directional antenna, is to suppress the signal in a given direction so that a station hundreds of miles away is not interfered with by your radio station. But there is no methodology. There's no method that we can use to measure the signal hundreds of miles away to say, well, we're really not interfering with that person, for several reasons. One, you'd have to get him to sign off in order to measure your signal. Two, a lot of it's at night where skywave is so unpredictable and unstable that there's no way to get anything that looks like a reading. If you've ever been reading a null you've ever tried to read a low level signal like at a monitor point in a null, and you're running late and it's getting toward dark, you'll sit there and swing a order of magnitude up and down. There's no way to read that sort of signal. So we're assuming, we assume that our local measurements are a proxy for the actual measurements hundreds of miles away where it counts. But again, this is a fiction we've agreed to tell ourselves. We don't know this for a fact. We're confident enough to where we know it works. We know that directional antennas actually prevent interference from other stations. And if a station fails to switch pattern at night and that sort of thing, often it's immediately recognizable even hundreds of miles away. So we know it works. But the point of this is that in a conventional proof, we have to take re-radiating structures into account locally when the evidence is poor that they actually affect the pattern hundreds of miles away, which again is where it counts. So with a mom proof, we can ignore most re-radiators, and that's good. So if we don't have to worry about a tower that goes up 5 miles away right next to a monitor point. Now we always have to go scramble to find another monitor point because that didn't affect the pattern where it counts, which is 100 miles away at the station we're trying to protect. So cheaper, no monitor points, no re-radiation issues. Good things for mobs. Did that work? Yes. Okay. When you have an array licensed with a mom proof, there's some things you have to be very particularly take into account. One, obviously, standard stuff for any array. Make sure the vines are off the tower, the ATUs are properly sealed, they're not full of wasps or rats. Don't let lawnmower man kill your coaxes. Make sure they're properly buried or supported, properly grounded. Coaxes on the towers are strapped down, that sort of thing. Make sure the controls in the phaser actually can be turned if they had to be. Don't turn them, but make sure they can be. If the knobs get loose, tighten them up, that sort of thing. Just the standard thing you do for any array. But again, the sample system is absolutely crucial. Be especially vigilant about your sample system. If you see something that happens, that changes in the sample system, go figure out what it is. If you're not sure what it is, leave it alone until you know. Bring in someone if you have to. Get a consultant. There are still people out there who know what they're doing with directional antennas. Some of them are in the audience today. There are others that are very, very good at this. I have some skill, and don't be afraid to ask for help. The professional forums on social media these days are very good. Some very knowledgeable people are there and happy to dispense advice, and most of their advice is good. Don't lose the original mom proof filing, as I mentioned earlier, because you'll need the reference point descriptions and measurements. You hopefully won't, but chances are you will. It probably wouldn't be a bad idea every 2 or 3 years to go around and measure them. Use that excuse of getting out of the office today. Make sure they're still there. They still read what you'd expect them to read. But the mom proofs are definitely a modern advantage, a good thing. Ron Rackley and Ben Dawson, and God rest his soul, Ron, and the others who were involved in that did the industry a very good thing, and we should salute them. And that brings us to the other part of modern directional antennas, or modern AM stations in general, and that is diplexing sites. There's no reason at all why one antenna, one tower can't radiate more than one signal at a time. And they do. And as real estate becomes more and more valuable compared to the radio station value, we see more and more sites consolidating. Mark Twain once famously said that real estate will always increase in value because it's the one thing the good Lord ain't making any more of. And I always thought that was pretty good. So you see more and more stations coming together, small towns, big cities, all in between. We just wrapped up a diplexing project here in Baton Rouge. We've got another one going on for a station in Alexandria, Louisiana. Some of the biggest stations in the country are diplexed. I was down in Orlando, Florida a couple of months ago, working at a site that had 250 kilowatt AMs that were diplexed into 7 towers. It was quite a very impressive site, and lots of coils and caps down there. A diplex site, either station can be non-D. The one we did here was non-D. It could be DA. Doesn't have to be the same number of towers for each station. Each tower does have to have a set of traps for the other station that's used. Not all stations have to use all the towers. But in general, the new kid on the block moving into an existing site has to, take the smallest piece of the pie. The towers are placed obviously to produce the best pattern for the original site, and the new guy on the block has to accept what's out there. This is where a good consultant will earn their pay, because a good consultant that can take the towers that are there and figure out a way to make a pattern that works as well as possible for the station who wants to move in. And this can make a huge amount of difference. But as more and more stations rely on translators anyway, we're seeing more and more stations accept whatever limitations they've got in order to get shoehorned in at a combined site. So this is a typical diplexer schematic. This is one we did here in town. This is I should have had a picture of the box. This is a really big 4-compartment box. We had Kintronics build it for us, but we built it out from there. There are, in this particular situation, there was an existing ATU also built by Kintronics that was in good enough shape where we didn't need to reinvent the wheel. So that ATU is still there. It has one more tuned network in it to help suppress the other station. But these are the primary traps here. They are series parallel resonant traps. At this is a 1260 was the existing. So these two caps here and that coil in series make a series resonant circuit, which looks like a short at 1260. But in parallel with this cap here, they are parallel resonant, which looks like an open circuit at 1460. So the 1460 energy here doesn't go backfeed there into the 1260 transmitter through its ATU, but the 1260 RF will pass through here to the antenna. And the same thing here in reverse, that this is series, these caps in that coil series resonant, and therefore a short at 1460, parallel resonant, and therefore an open at 1260 there. And then this is a secondary trap in reverse, series resonant, and therefore a short to ground at 1260, parallel resonant, and therefore an open circuit at 1460. And then this is just a conventional ATU to take the impedance here back down to 50 ohms for 1460, which is the new station that moved into the existing 1260 site. Very straightforward. But it's all coils and caps. It's not magic. But you do have to competently design the traps. The design is not trivial, and trying to come up with matching the design to the real world available parts is also not trivial. The people who do that well, and I'm barely good enough at it to claim it. People who do that well, again, like consultants and directional antenna patterns, definitely earn their pay. One thing to note is that all of the magic in a diplex site happens at the bases of the towers. Back in the building, typically there's no difference at all. Every now and then you'll have a situation where you'll have to add a bit of a trap in a phaser, typically a secondary trap shunt to ground, in case there's any energy that managed to make it back that far from one of the towers. But all the traps, all the magic happens at the in the ATUs at the base of the tower or towers. As I showed you with the schematic, there's always primary traps, which are series traps. That's the first thing you have to do is block out the other stations RF, not shunting it to ground, because then that would make it a parasitic element. Block it out in a series fashion first, and then anything that makes it past that, you can shunt it to ground with a secondary filter. Another thing to note is that in diplexing sites, the traps, not necessarily the ATUs, but always the traps, you could only use vacuum capacitors because, and most people don't realize this, mica capacitors are not temperature stable enough to be used in traps and to be considered stable to maintain the trap tuning. Some of the traps are very, very high Q, very, very sharp tuning. And so a tiny change in capacitance will screw up the tuning of the trap. Also, the closer together the stations are to each other in frequency, the higher the Q, the narrower the filters, and the higher the voltages, the higher the circulating currents. No, I have that backward. Well, the higher the voltages, possibly the higher the circulating currents. And you have to take this into account. High voltage rating vacuum capacitors are not cheap at all. And diplexer design, as I said, is an art. It's a study in compromise. You have to consider the cost of the components. You have to consider the availability of high voltage vacuum capacitors. You have to worry about the Q of the networks. You have to worry about the bandwidth and the phase rotation back to each transmitter, lightning suppression, arc suppression. There's no substitute for someone who knows what they're doing, and there's no substitute for using the proper parts. Sometimes you can take a phaser that's being decommed or something like that and take a bunch of the parts out of it and build the diplexer out of it. I've done that. I know people who are masters at that, and I could name some names. And again, it's a matter of knowing what you're doing. That's often possible, but don't skimp on the design. Don't skim on the construction of a diplexer. It'll bite you in the butt. The voltages in diplexer series resonant networks are very, very high. We routinely see voltages with the safety ratings, appropriate safety ratings of vacuum capacitors of 40 or 50 or even higher kV across a cap. Sometimes you have to use 2 caps in series. You have to make sure they're up on very tall insulators and the Corona caps on the insulators and things of that nature. We were involved in one in Dallas a few years ago. It was a 50 kilowatt, and the voltages were scary. We ended up having to do things like put 2 megohm, 2 watt resistors across each. We had 2 vacuum caps in series to get the voltage, and we had to put 2 megohm resistors across each cap in order to equalize the voltage. Because what would happen is that things like the film on the surface of the capacitor for when someone had handled it, the nose grease, hand grease, skin oils on a capacitor would force the voltage on one, would have a little more leakage on one than the other, and would affect the voltage so that one cap had more voltage on it than the other, and that cap would spit arc across it. So we had to actually equalize the voltage on the 2 caps with bleeder resistors across it. And that was scary to all the mitigation measures we had to come up with to make that work. And that's uncommon, but it's not unheard of. Pretty tough stuff.
Hey, Mike, talk a little bit about the complexities of diplexing stations that are directional. I know you worked with us one here in Montgomery where we had a 2-tower directional that we diplexed to non-directional, but it was difficult. You could make the transmitters happy, but the pattern would be off. You get the pattern right, and the transmitters were not happy. That's a little some things you have to do to make both of the arrays, especially directionals, work properly.
Yes. When you have a diplexed directional site, that is the toughest thing you have to do, because then you have to worry about, as Larry noted, you actually have three things you have to worry about. You have to maintain the suppression so you don't create spurs. You have to maintain the VSWR back to the transmitters so that the transmitters are happy, and you have to maintain the directional pattern out in the field. When you diplex directional sites, you also have to worry about isolation between the 2 sample systems. The conventional AM19 series monitors are wideband. So you had to be very careful about where you put the sample devices. You had to put them in front of the traps, the last traps. But then you had issues of whether that was actually an accurate representation of what went into the tower or not. And so you end up having to build I would say that two separate sample systems, one for each station. If you had loops on the towers, then you had to have traps in the antenna monitor, the sample system itself, and that's a whole different subject, because then you have to certify the phase shift through the traps. Modern antenna monitors, like the 1900 series from Potomac, are narrowband, but even they have to be specifically designed and set up for a diplex site. But yes, Larry's right that then you have another variable to worry about, because a series resonant network, the primary trap, there is some phase shift across it. And a tiny bit of difference there in the tuning will affect the suppression and the parameter set, the phase shift through it. So the first thing you do is the tune for suppression. That's number one. Then you go back to the phaser and you tune for the pattern. And then number three, you go back to the input to the phaser matching, common point matcher, and make the transmitter happy. If you've got a one station is non-directional, then you can do it in the ATU at the base of the tower. But there's a lot of variables, there's a lot of iteration, there's a lot of back and forth. And Larry and I, spent all, as I recall, all weekend getting this diplexer happy. And that was after someone else had done all the physical installation. All we were doing was tuning. And it was not trivial. If you're doing the design, if you're building it from the ground up, then there's quite a bit of iterative process to walk it in and make it happy. So Larry, does that answer your question there?
Yeah, I just knew that we fought that for a while, and I saw that as something that we probably needed to talk about, is the complexity of it. And then if you add into the equation another thing you want to talk about, and you may have this in some of your slides a little bit later, but if you're dealing with a negative tower, that's I know we ran into that at the 50 kilowatt over in Georgia.
Yes, that 5-tower array, 2 of the towers were negative. And one of them was hugely negative. It had like 10 kilowatts and injected back into the phaser, which is a remarkable amount of power for a negative tower, but it was a 50 kilowatt. If DAs are voodoo, the negative towers are voodoo squared, because many people don't understand the concept of a negative tower. But here's how it works. In a directional array, most of the time, we feed power to both towers, or all the towers, and they all radiate. But in a directional array, each tower has what's called a self-impedance. That's the impedance it would have if it were the only tower in the field. And then between any two given towers, there is a mutual impedance. There's the coupling between one and the other. And depending on how you feed the power to each tower in an array, the resultant impedance at the base of a tower, which is the sum of the self-impedance and all the mutuals, the coupling back from the other towers, you can have a situation where a given tower ends up injecting, pulling in power from the other towers as opposed to putting it out. So instead of sending power to that tower, you're actually taking it back. Now you honestly could just tie off the tower into a dummy load and burn up that power. And I know 1 or 2 stations in the country, one of them in Scranton, Pennsylvania, if it's still there, that they did it that way, because otherwise they couldn't make the bandwidth work. But the traditional way to make a deal with a negative tower is to play with the phasing in the system so that power is carried back to the phaser and injected back into the system. It's recirculated, if you will, because otherwise you have efficiency issues. You don't want to just throw that power away. That's just literally burning up a dummy load, not putting a signal out there to the people who are going to fill out books and patronize your advertisers. But a negative tower and a negative phase reading, not the same thing. Any given tower in an array could have a phase that's positive or negative relative to the reference. It has nothing to do with negative towers. A negative tower is one that injects power back into the system. And yes, the phasing has to be 180 degrees out for that, because the power flow is going backwards. And if you actually put a bird meter, if you will, in the transmission line to a negative tower, you will see forward power going back, if you will, more reflected power than forward power, if you want to think of it that way. Power is going back into the phaser. This really isn't any different in a diplex site. You just have to, again, be very careful. You have to maintain suppression first, parameters second, VISWR third. But negative towers are definitely one that is often misunderstood. And if you have a tower that's barely negative, that's the worst one, because then you may have to adjust it where the power can flow either way. I've seen arrays where there was almost zero power flow in a tower one way or the other. And there are special tricks you can use in a phaser to allow you to be able to feed power one way or the other, in or out of a tower, various tricks to it. But you hope if you have a negative tower, it's solidly negative, because the ones that are just barely negative are the hardest to deal with.
I think the one in Macon had one that was almost right zero. And
it did. It had one that was hugely negative and one that was fairly close to negative. And we had to take special consideration of that in the phaser. I did a design in Detroit a couple of years ago. It was a 6-tower array, and 2 of the 6 were right at zero. And we managed to make it work. Hats off to Mike Van Hooser and Ed Lively, who actually tuned that one up in the field. But that was a challenging design and a challenging implementation. So, and then it's not rocket science. You know, it's just electrons. It's just, you know, coils and caps. One thing to note is that not all arrays are eligible for bomb proofs. Bomb proofs are not applicable to any shunt fed towers or any that includes folded unipoles, because the base impedance is too unpredictable, and we're unable to model it. Towers within certain height limits have to have voltage sampling devices at the base instead of current sampling devices. These are much more expensive. Kidtronics does make them, but they're like $3,000 or $4,000 per sample device, as opposed to $500 per sample device for a delta toroid. So there are limitations, but most stations are eligible for bomb proofs, and more stations are doing bomb proofs when they have to do a proof. We did one last year in Birmingham, the one I mentioned earlier, and we ended up going back with a conventional proof on that because we would have had to have done voltage sampling devices, and the decision was made that it just wasn't cost effective to do that. That was one of Frank Giardina's stations. I see he's managed to step away from his camera, but his feed is still up. So I presume he's listening. Diplexing is more and more common. We're going to see more and more of it as we go along, as AM sites are converted to more cost-effective solutions for the real estate that they're on. If you're involved in a diplexer or a diplex situation, find a good consultant. Make sure he knows what he's doing. Follow his suggestions. Get him or a reputable firm to do the proof, to build the boxes, diplexers, anything of that nature. Also remember, if you are a station engineer, that you are often the only technical person in the loop and the only liaison between the owners and the vendors. That puts you in an uncomfortable position. A lot of times, owners these days regard engineers as a necessary evil, as a cost center. They wish we would all go away until they need us, and then it's, you know, why are we not back on the air? But you know, it's up to you to be an advocate for the people that are doing the work, and to make sure that the job gets done right. So when at the end of the day, you can build a good site, you can take pride of it, and then go home to your family, because no one's tombstone ever said, I wish I'd spent more time at the transmitter site.
if anybody's got any questions they'd like to ask Mike, just hop on the chat down at the bottom of your screen and type them in, and we'll share that with him. One other thing, that have you had any dealings with stations that are looking at or trying to go digital AM and trying to broadband these systems to pass the digital?
I have not recently. I have been involved in broadband ATU and phaser design for 35 years, and wrote various pieces of software over the years to accommodate that. I have not been involved in the latest round of digital only AMs, but broadbanding with diplexing is challenging. It's not impossible. The diplexer we did here recently that I showed the schematic for earlier, we were able to achieve a good symmetrical sideband impedances on both stations, and we're very pleased with that. Now, neither of those stations is doing digital, but if they wanted to, they could. Again, it's a matter of proper design, proper techniques. You get what you pay for. You hire a good consultant, and you let him do his job.
An interesting thing I saw a while back was there was 3 stations diplexed onto one tower, and if you had all 3 on, the power was bouncing around. If you turned off one of them, the other 2 would work, and it didn't matter which one you turned off. It was just if you had all 3 going, you would have some bouncing around of the power. But if you turned any one of the 3 off, the other 2 would settle down.
Now, when you say bouncing around the power, you mean you're looking at the actual power output of the transmitter kicking back and forth?
Yes.
I would have to investigate that. Off the top of my head, I don't know what would cause that.
Well, they were saying it was because of the filtering system was not really set exactly right, and if you tried to have all 3 of them on at one time, it was affecting something and causing it to bounce around.
Well, that would be my first thought. Yes. Now, I've seen on several situations, in fact, 2 different diplexing sites that we were involved with, one here and one in Columbus, Georgia, where they use the BE transmitters. And one of the things the BE transmitter does is it looks at when it looks at VISWR, it's actually looking at forward versus reflected power as a ratio. So we found that we had to start the transmitters in a specific order for the different stations, because otherwise one of the BE transmitters, seeing the tiny bit of VISWR coming back from the other station starting first, wouldn't let the transmitter come on, because it thought that it had an unacceptable VISWR, even though it was milliwatts worth of power coming back. But compared to the fact that the transmitter itself was off, it was looking at this ratio of almost off to almost nothing and saying, oh, too much VISWR, I can't start. But if you started that transmitter first, then the other one would start, which was not a BE, without any problems. And here there's 2 BEs, 2 5-kilowatt BEs. And when you start one of them at low power, it gives you a VISWR warning. But when you kick it up to high power, the VISWR warning clears. Now it'll start, but it'll give you a phantom VISWR warning, even though the suppressions are right and everything. So transmitters are sometimes very, very picky.
John, you have any comments for Mike or questions for Mike?
No, I really don't. This was quite a good presentation, and I always learn stuff out of it. So I just finished fighting a similar situation with a diplexer, and we had issues between a 10 kilowatt and AM, and they were both Bs, and they both had to go on in a certain order, or they wouldn't go on. I thought I was nuts, so I'm glad to hear that.
No, I've seen that on a number of occasions. So I see that in the chat here. Let's see. It's someone says John Markin, so if I'm pronouncing that right. So Marconi. My first experience with AM directional arrays does not have phasers, just matched networks in the ATUs, adjustments made using a variable vacuum cap and tap on the coils. For a simple 2-tower array, do you really need phasers? Well, yes, you have to have something to do the job of the phaser. The job of the phaser is to split the power between the towers and to adjust the phasing. As I mentioned earlier, there were some consultants, especially Earl Cullum from Dallas, who's been dead for many years, who loved to build phasers that were basically nailed to the wall. In one case, literally, KAAY in Little Rock was one he did, and the phaser was an open frame phaser at the base of the center tower, and there was not a single adjustable anything in the whole thing. It used the very, very old technology built in the 50s. It was very, very old technology of big capacitors that looked like something out of a milk jug from a farm. They were about a foot in diameter, about 2 feet tall, and they were pressurized with nitrogen. And they were progenitors of today's vacuum capacitors, and coils with taps that you had to screw it out and move. The damn thing was stable as hell, but when you had to adjust it, it was not pleasant. So that's the trade-off that you make. But yes, if you have just a simple 2-tower array and one tower has much more power than the other, then you could literally take the ATU from that off the bus, if you will, off the power divider bus, and then just tap the other tower off of that, sometimes with as little as a coil to ground and a series coil and cap, depending on the base resistance of the other tower and the length of the transmission line. You can build a phaser with as few as 2 or 3 components, but it's still a phaser. Something has to do that job. Okay, so here's the next question. Any recommendations for an AM reception antenna? Yes, ask your Stady, I guess, people to allow you to monitor FMs instead. No, but seriously, I've heard that Baylor has not been answering their phone some lately, so I'm not sure their status. John, do you know if they're still?
Actually, I just spoke with one of the gentlemen up there the other day. We actually didn't talk on phone. We talked about email, and they are still in business.
Okay.
They did make an antenna at one time. Both Innovonics has an outdoor ring type weatherproof antenna, which seems to work very well. And then there is I think it's not DM. I can't remember. There's a company that really does a lot of work for amateur radio operators. I believe they're in Indiana, Ohio. I want to say it's DM Engineering or Electronics.
Or DX Engineering or something like that.
Something like that. And they make an AM antenna for outdoor use. Both of those manufacturers, you're easily going to spend, same thing with Bellar, probably in the neighborhood of $500 or $600.
Right.
Of course, you could always wind your own.
Yeah, there's various ways to do that.
I think you had one other question up there concerning MOM data to track the degradation of an antenna array.
Yes, catastrophic disappearance of the radials. Most of us have been there these days. Many's the time I wish I could put a sign at a transmitter site says, dear meth head, if you're in serious need of a $50 fix, here's my phone number. Please don't screw with my ground system. Of course, that wouldn't work, but it would be a nice thought. Theoretically, the base impedance of a tower changes as the ground system gets better or worse. Of course, they never get better on their own. How that corresponds with how well the station gets out, I don't think there's really much correlation there. Again, you're developing the model. The model will allow you to generate a set of parameters that we theoretically agree will produce a pattern, but that doesn't take into account the degradation of the ground system. It's very difficult to actually obtain meaningful data about the degradation of a ground system, in my experience. The only way to do it via accepted methodology is to make a full proof and an analysis of the actual inverse field, and then the RMS field of the whole thing around the pattern. That's a lot of work. And when it's over with, it's like, well, the ground system isn't what it used to be, and that'll be $12,000. Thank you very much. Just if there's any question about a ground system and the budget is there to fix it, put in a new ground system, put in a few new radials. You'll spend a whole lot of money to obtain an answer you probably knew already.
That's right. But Mike, we sure appreciate your time today, and you had some most valuable information for everybody. And I'm sure if you want to give people your contact information, if they have questions, and they can sure drop you an email or something.
All right, well, that sounds great. That's the one thing I didn't do, was do a closing slide on my presentation, but it's mike@michaelpatton.com or Mike Patton on Facebook. And I'm on most of the professional forums. I'm not hard to find. And By the way, John, it is DX Engineering.
I
and
just looked and that is correct. It's Engineering, and then they're in Talmadge, Ohio. They have a good
Yes.
web presence if somebody wants to look them up.
And I have used some of their stuff at my home. I have one of their combo AM FM antennas on top of a pole at my house, and it does fairly well. So good folks.
All right. Thanks again, Mike and
right.
John. Glad you could join us today as well. And want to mention to you real quickly here that our next seminar, webinar that will be coming up September 21st, we'll have Kirk Harnack. He's got some information concerning some of the newer audio over IP consoles that are out now. So be sure to join us on September 21st for that particular webinar. So thanks everybody for joining us, and we'll see you again oh, that's the wrong slide. We canceled that, by the way. I forgot to change that slide. That the ABA convention is actually moved to January, as are a lot of the conventions and everything that are going on that's been canceled because of the increase in COVID problem. So thanks again for everybody for watching, and we'll see you in September.
All right. Bye-bye.